All right. Good morning or good afternoon, everyone, depending on where you join us from, and welcome to this Nano in Action webinar organized by the Nanotechnology Industries Association. Today's topic is graphene solutions for societal challenges. And before we jump right into the subject matter, I wanted to take a minute to briefly introduce the NIA and our activities. We're an industry association based in Brussels with offices in the UK, Switzerland, and the Netherlands. And we have as overarching goal that of supporting the successful development and commercialization of nano-based solutions. And in order to do this, we support our members in, first of all, understanding what kind of requirements their products have to comply with in order to be placed on the market. We foster confidence by end users in nanomaterial safety and performance. And we try to create a platform for exchange where all the different actors in the nano ecosystem can find the right interlocutor, be they suppliers, clients, or researchers and innovators. And in order to do this, we participate in the policy and advocacy discussions to make sure that the regulatory framework that develops is appropriate for industry to thrive. We provide our members with opportunities for visibility and networking, and we try to contribute to the building of that nanotechnology ecosystem that I was talking about earlier, so that all the different actors in the process can talk to each other and understand each other's needs. And that is why among our members, we do not only have the producers and users of nanomaterials, but also the research institutes and universities that work on early research and innovation before the commercialization phase, but also the providers of those collateral products and services, such as support for regulatory preparedness and lab equipment. Now, in terms of regulatory and policy work, we have a part of the work that is for the benefit of members and goes in both directions. So on the one hand, we keep members informed of the relevant developments and their potential impact for industry. And on the other hand, we bring companies' voices into those stakeholder forum where we participate both at EU and OECD level, as well as in the relevant standard developments at CEN and ISO. We also have a part of activity that is aimed at the general public as well as policymakers, and we usually publish materials that are available for free on the NIA website on this. We're currently working, for instance, on a position on the hot topic of safe and sustainable by design. In terms of the platform and networking that I was mentioning earlier on, there is, of course, the webinar series Nano in Action that you are joining today. And it will be no surprise to anyone that most of the activities over the last couple of years have happened online. So we have managed to grow our LinkedIn community to over 15,000 people. But we are slowly but steadily coming back to in-person events as well. So we have good hopes of managing to organize our annual symposium in Brussels in the second half of the year. And in the summer, we will already be participating in a number of trade shows, including with an exhibit space called the Nano Pavilion. And finally, we're involved in a number of EU projects that support notably work on safety and the development of test guidelines for nanomaterials. Now, in order to get involved, you can, of course, register for a newsletter, which is a monthly free of charge newsletter. You can join that LinkedIn community that I mentioned earlier. You can join us on Twitter. And of course, if you don't want to be just a recipient of information, but you want to actively participate in shaping the content, you can also reach out to us if you have any questions about how to join the NIA. Now, on to today's topic. So I'm going to introduce the first speaker in a moment. His organization was actually a bit the inspiration behind this webinar, because graphene is actually one of those nanomaterials that probably also the average person has heard about. They might not know exactly what it does and how it works, but they may have heard of it. And indeed, within the industry as well, there's still some lack of clarity on the different types of materials and how to classify them. And that is why at the end of last year, the Graphene Council released a Graphene Classification Framework. And I'm happy to introduce Terrance Barkan, who is the Executive Director of the Graphene Council. I'll give him the floor in a minute to present the framework, the rationale behind it, and the next steps that the Graphene Council has in mind for the framework. So with that, I will stop sharing my screen and invite Terrance to take the floor.
Thank you very much. Appreciate this opportunity. So good afternoon to everyone. Just let me get this full screen here. And is the screen visible for everyone?
Yes.
Okay, excellent. Well, thank you again for this opportunity. We're going to focus on something very specifically, and that's the Graphene Classification Framework that was published in December and that has continued to be used. And give you an update. We want to share with you what it is, why it was developed, and how to use it. And so just briefly to talk about the Graphene Council, if you don't already know who we are, we connect about 30,000 material scientists worldwide, 1/3 in academia, and 2/3 of them are commercial. And there are a lot of other things that we do, including working on standard, which is the focus of today's presentation. This is a list of some of the members that we have in the Graphene Council. And just like NIA, we represent research institutions, graphene producers, and end users globally. So the Graphene Material Classification Framework came about because graphene is being used commercially more and more every single day. But there's a lack of understanding of the different types and forms of graphene. Now, from a scientific perspective, graphene is simply a single atomic layer of sp2 bonded carbon. But as far as commercial application is used in the way it's used in everyday commerce, graphene is actually a whole family of materials which can include things like graphene oxide, reduced graphene oxide, nanoplatelets, functionalized material, etc. And one of the main impetus for us to work on this classification framework was that when we were engaged with regulators, whether it be in the European Union or if it be in the US, that we found that the scientists who had to make judgments about these materials, because it was so new, they also didn't have a deep understanding or sensitivity to the different types and forms of materials. So regulatory side was an important impetus for us to do the classification framework. Now, the Graphene Council, which was founded all the way back in 2013, so we're almost 10 years now in existence, have been involved in the development of standards through various bodies, including ISO, ANSI, IEC, ASTM, et cetera, BSI in the UK. And what we did is not to start from zero, but to work on the existing standards, both those that have been published, which are listed here, and those standards that are in process in working groups and will be published in the near future. So that was our baseline. The Graphene Classification Framework was intended to make an extremely easy and clear way of comparing any form of graphene, and that's regardless of how it was made and also what feedstock material was used. And there are no fewer than 14 different methods of graphene production that have been identified within the framework so far. We also recognized that producers were not issuing the same set of data about their materials in the form of their data specification sheets. And when they don't include the same information or put it in the same format, it becomes literally impossible for an end user or a consumer to compare one material to the next based on these technical data sheets. And so we wanted to provide a standardized way and a minimum set of information for all, excuse me, advanced graphene producers to use. And we also want to understand how to take the different characterization values, what kind of aspects, layer count, lateral size, chemical composition, and how does that apply then to commercial application. The other thing, as I've mentioned, we were always thinking, who is our audience for this? And this is a very useful framework that benefits producers as well as their customers and regulators. So that was really important for us to think about how this can be used across that spectrum. And we only focus on those commercial aspects. There are some standards, for example, a blank detail specification sheet, which has more than 75 different measurands for graphene that are possible. But when we looked at what is commercially relevant, a much smaller set of 19 variables were identified within this. And those 19 include a couple that are only valid for specific forms of graphene, like CVD, monolayer, single layer graphene, versus what's referred to as bulk graphene that people will know as a black powder or a paste that's made of multiple layers of carbon, but is still a form of graphene. And then the last point on this slide I want to emphasize is we took our baseline out of the existing standards bodies. We created the classification framework, and we have now licensed this back to ISO so that ISO can take it and put it into a formal ISO standard that will be used universally around the world. So we're giving back to this. This is not something the Graphene Council is trying to monetize or to monopolize. It's something we're giving back to the community. So how do we do this? We started in April of last year with 100 volunteers that represented academics, graphene producers, graphene users, and regulators in this from around the world. We use what's called the Delphi process, whereby we did a very rapid iteration of putting out a proposed framework, received feedback, developed consensus, and then moved to the next pieces. And this allowed us to do a tremendous amount of work in a period from April to where we could publish it in December. And literally, I would argue if this had gone through the traditional standard setting process, it would have taken at least 3 to 5 years to come up with the equivalent body of work. And I'm not bragging on that. I simply want to say that we used a different process that was rapid iteration. And we also had a large peer group to work on this, and it worked extremely well. So what's in the graphene classification framework? Well, first of all, we identify those material characteristics that are most relevant for commercial use. We've identified what methods of testing should be used to identify and add values for each of those characteristics. As far as the values themselves are concerned, we've identified a range of expected values for each of the characteristics. And then another part that we did, there is an existing ISO standard for nomenclature for definition, but what we introduced was a syntax on how to name the particular material in a consistent way. Commercial producers of this material will often introduce bespoke terms or names and trade names, which we are perfectly supportive of from a marketing and commercialization perspective, but they're not generic and applicable to all materials, and they can in fact be slightly confusing, especially if you go to a regulator. These trade names don't really mean anything. We wanted to have a generic, consistent way of referring to these materials so that in a simple one-sentence description, one would have an extremely good idea of the type and nature of graphene that you have. And then finally, we formed a template of a technical data sheet formatted to the Graphene Classification Framework, and we offer this template out to companies to use for their technical data sheet. And I'll talk a little bit more about that in a second. On this slide, you see a visual representation and summation of what the graphene classification actually includes. And we thought this was another aid to understanding it. So on the left, you see this list of 19 values that are applicable to classify or to determine what form of graphene we have. And I also want to emphasize the classification framework is not intended to determine if a material is superior or inferior, if it is quote unquote good or bad or quality or not quality. It is simply to identify and categorize what type and form of graphene there is. And for anybody who's worked with this material, you understand that one form of graphene that might be ill-suited for one application might be excellent for another one. So it's all relative in how you use the material. So these 19 aspects, and I'm not going to go in detail on the 19 aspects, but I want to make you aware of them, are what have been identified based on literally years of research and evaluation and questionnaire and interfacing with the community on what is most relevant commercially for the most forms of graphene. And you'll see, for example, the first two listed here, the production method and the raw material used, these are actually self-declared values. They're not tested for. And then you have another 17 that would be the result of different testing. The syntax gives you a structure for how to refer to the material in a consistent manner. And then we have the technical data sheet. And so this is kind of what it looks like. So for example, a mechanical exfoliation that might use graphite that results in a powder form of the material. And then you have additional tests that follow to interrogate the material. sp2 bonded carbon is a level of defect, a layer count, lateral access, vertical access of the material, etc. So you have all these different measurands, which also should make it crystal clear to everyone. Now you know why there are so many different types and forms of graphene material, because you can have any combination of these different values. You'll result in a different morphology and chemical composition of the graphene in question, which then performs differently depending on the application. So that's the complexity that we're trying to codify with this classification framework. And then here, I just want to give an example of the syntax. So for example, we talk about layer count, lateral size, particle shape, oxidation, whether it's oxidized or not, whether it's functionalized or not. And for those of you who may or may not be familiar with the term functionalization for graphene, it simply means an intended process which adds another species of elements or molecules to the graphene itself to improve its performance on a certain behavior. It might be for dispersion, for example. So functionalize is an intentional changing of the composition of the material. What form is it in? Is it in a powder? If it's in a solvent, what solvent is used? What method of production was used? If it was a CVD process, for example, raw material, was it methane gas, etc. And so here's an example of how this might be used. Is you have a freestanding monolayer sheet of non-oxidized, non-functionalized graphene produced using methane gas and a chemical vapor deposition method. That gives you a good idea of what material you have. A different example might be a very few layer, highly oxidized, non-functionalized graphene powder produced from graphite using a modified Hummer's method. So, these are different ways of describing a material generically that give you a pretty good sense of the material you have. The syntax is not intended to replace the full characterization and the technical data sheet. It is simply offered as a consistent shorthand on how to describe a particular material. And then when we go to the data sheet, it's pretty comprehensive. It includes all of the different dimensions that are in the Graphene Classification Framework. It includes additional dimensions that some producers may wish to add, things like color and odor, which are typically on a technical data sheet, but are not critical for commercial use. That's why they're not in our Graphene Classification Framework, but you can add them as a producer if you wanted to add those values. And then we have imagery, including Raman, AFM, SEM, TEM images that should be on any technical data sheet, in our opinion. And so we offer up this format of technical data sheets for companies to use so that they will then be consistent in commercial use. This is all part of the Graphene Classification Framework. And I'm coming to a close on my short presentation here. I'll be happy to take any questions when the time is appropriate. But just to run through what we did, we started in April 2021. We went through all the consensus process. We made this classification framework publicly available on December the 2nd. In February, we signed over copyright rights to ISO, and the first meeting of the working group to convert the Graphene Classification Framework into a formal ISO standard has already taken place. And now what we are doing is a series of material characterization testing. And the end result is we are going to produce, we as the Graphene Council, together with laboratories that we work with to do the actual testing, we are then going to deliver technical data sheets for 5 different companies. This is what we're working on today, right now. based on the Graphene Classification Framework. So this is more than theoretical. We are putting this into practice and into commercial use. Now, what's next? We're going to provide a separate document for laboratories that want to do Graphene Classification Framework testing so that they know what sequence of tests would be performed. So without going into too much detail, of the 19 measurands, one method of testing might result in several of those. So for example, using XPS to test a material will give you chemical composition. So that would give you any impurities and trace elements, carbon content, as well as oxidation and functionalization. So for example, that one test can result in several values, and that's why the guide for labs would be for them to test in a different sequence than the values appear in the classification framework. We also want to work on developing what would be the carbon footprint for the production and use of graphene materials. As more and more companies go into net zero, they're going to want to know if we use graphene, what is the net impact from a sustainability point of view? And graphene has a tremendously positive in application. And so we want to make about the full impact measured of graphene in work. For example, in February of last year, Health Canada had an issue with graphene enhanced face masks. The Graphene Council within 1 week had a formal position back to Health Canada, who then reversed their ban on the materials based on information in part that we provided, including testing of the face masks and providing them with that data. And we will continue to determine what is the proper handling of graphene materials, which any material has some health and safety toxicological aspects to it. Even water would have that if you have too much of it. So the question is simply, what is the right profile for this material and how to handle it? And then we continue with standards. If anybody would like to get involved, this is open to anybody. You don't have to be a member of the Graphene Council. We just ask for your expertise, and there's a way to participate as we continue to work on these standards. And so in conclusion, we expect leading graphene companies are going to use the classification framework to separate themselves from less transparent competitors. We think that customers can use the framework when going for a supply contract to define their requirements. So for example, if you have a company that requires graphene for batteries and they want a second source of supply, they can now go with a very specific detail of the type of material that they need to potential suppliers. Regulators can use this to better understand the different types and forms of graphene. And we assume that groups of morphologies of graphene will have similar toxicological profiles, which means it makes it easier for us to group these materials based on their toxicity or potential toxicity. And that means we can handle the materials appropriately based on the grouping that they fall into, such as a graphene oxide versus a graphene nanoplatelet versus quantum dots, etc. And the last thing I want to emphasize is that this whole framework has been built by members of the graphene community for use in the graphene community. So this is really closely tied to real-world needs and real-world expertise. This is a short list of all the things that the Graphene Council does. I won't belabor that. I just offer that up if you're interested to learn more. And if you want to contact me, I'm always open to talk to anybody about graphene or other advanced 2D materials. And I want to say in conclusion, as I stop the share, thank you for this opportunity to speak with you about this topic. And I'd be very, very interested to get everyone's reaction to it and any questions that you may have.
Thank you very much, Terrance. That was very comprehensive. And as I mentioned, if anyone has questions, please put a pin in them and we'll take them all at the end. Now, it's interesting you finished your presentation talking about real world applications, because that's indeed what we are going to tackle in the second part of this webinar. And I just want to mention, of course, we are aware that societal challenges and tackling all societal challenges in a 90-minute webinar is far too ambitious. So we have obviously not even attempted that. We just picked a couple of examples, but really to show that we have graphene-based solutions that are already applicable to today's issues. So the first one we picked is energy. And so energy obviously has been very much in the headlines this last week because of geopolitical developments. But as you know, indeed, it is one of the key sectors in climate action strategies globally. So it is one of the sustainable development goals that we should try to achieve by 2030. And just to give a couple of data points, in the EU alone, the energy sector, so production and use of energy, account for over 3/4 of the total greenhouse gases emissions of the bloc. So it is obviously decarbonizing the energy sector will obviously be a key part of achieving climate goals. Something that the European Commission has recognized and adopted key targets for 2030 that are quite ambitious. So a cut of 55% of the emissions taken 1990 as the baseline year, increasing the share of renewable energy to up to 40%, and also increasing improvements in energy efficiency by 32.5%. And that 9% additionally is bracketed because the Energy Efficiency Directive is currently being revised and the draft legislation is within the European Parliament at the moment. So we will see how much that gets increased. So with that, I would like to introduce Dr. Anna Molta, who joins us today from Talga Technologies, where she is head of advanced materials and technologies, and will talk us through where graphene comes into the picture when we're talking about energy solutions. So Anna, welcome, and whenever you're ready.
Thank you. I'm not sure if others were struggling a little bit in the previous talk with the audio at one point. So I'm wondering if I would keep my video off for the duration of the talk. That might
help. Thank you.
Okay, I shall do that then. Can you see my presentation?
We can. It's not in full screen mode yet, but we can.
There we
and
go.
Now it is. Thank you.
Okay, very good. So thank you, Chiara, for the introduction and for the opportunity to talk about graphene in energy. I've mainly focused on energy storage in this presentation, but just very, very briefly touch on a few other topics as well. I'm going to be first giving you an introduction to who we are, who is Talga, why am I interested in this in this area, and then talk a little bit about battery basics, just to put it in context what we are talking about with the opportunity for graphene to come into this space. My name is Anna, and I look after research and development into new materials, and this is wider than graphene, but that also is going to become obvious in the next few slides. So let's see. There we go. So Talga is a company that has a really, really big ambition. We are headquartered in Australia, but all of our operations otherwise are based in Europe. So we say we are vertically integrated, which means that we own a graphite source in Sweden. We mine it, we process it, we produce advanced materials from it, and in our product development, we target novel technologies with sustainability high in our thinking that are applicable in multiple areas. So in Sweden, this is mining and currently also graphite anode production. In Germany, we have a graphene production facility and process development unit. And in UK, where I'm located in Cambridge, we have mainly R&D and sales activities. So what we do, so we start with a very high grade graphite. So this graphite has has the highest, the ore itself has the highest graphite concentration of all the active mines around the world. And we take this ore, we process that into purified graphite. So we need to remove the other minerals from the material, and we've developed process technologies around that. So in order to first of all get the best out of our material, but also to keep the purification process, which is often quite a big source of chemical use and waste and energy. So we are trying to develop, and we have developed and trying to further improve on methods that would be more environmentally benign. We also have developed a process of creating a graphite-based anode material, multiple other graphite-based battery materials, and a process technology to make graphene. So Terrance just mentioned how graphene can be made in many different ways. So we are doing this top-down process where we take graphite and we liberate layer by layer graphene from that raw material. So we also have process technology for the functionalizing, also something that Terrance mentioned, and this is really to make the graphene product more suitable for the final application. So the areas that we are particularly targeting is energy storage. So we have multiple active materials for batteries, lithium-ion batteries being the most researched and developed area in our portfolio, but others as well. We also look at graphene materials, particularly for conductive additives, protective and anti-corrosion coatings, and composite applications. And in these applications, we are often focusing on longer lifetime for the products. We are focusing on maybe lightweighting products or improving the recyclability. So in all the way through our product portfolio, sustainability is very high in our values. So what do we try to do? We try to produce the world's most sustainable batteries and consumer products through multiple graphitic materials. And what helps us on this path is the high grade of our graphite that we own. This is quite unusual for a graphene company to also own their own resource. So we are very privileged to be in this position. The processing technologies that we use, in Sweden, in our the area of activity, we are fully covered with renewable electricity. So the CO2 emissions that we generate in our activity are very, very low. And as mentioned before, we have that leading thought of sustainability through our product development activities. So that's what we do. Chiara mentioned that the European Green Deal and the significant effort the EU has identified that we need to do to avoid the environmental disaster crisis, catastrophe, as whatever you want to call it. But it's more than a challenge, I would say. And to put it in context, during these last two years of COVID disruption to production, to transport, to travel, the level of reduction in the greenhouse gas emissions that we need from now to 2030 to reach this goal is to year on year do the same as we've had in the COVID period. So it is a significant shift that we need to face as a society as a whole. So the image here is from the Green Deal website. And so, of course, there is a significant effort needed in multiple sectors. But what is in focus here today with the energy talk is the area of globally competitive and resilient industry and cleaner energy. So in order to reach the goals, It was already mentioned that energy generation and use accounts to about 75% of the greenhouse gas emissions. So, so here we are looking at reducing that number significantly through choosing cleaner energy sources, so renewable energies. Maybe nuclear comes into play, and many other new energy sources are being developed as well. But also what is really important is energy storage. Efficiently store energy and make it available where it is needed. Important part of this is the fact that that energy storage that amounts to in the current market mainly to batteries. There are others as well, supercapacitors, other things, but batteries is a key enabler in this space. Batteries are by and large produced in Southeast Asia these days. So, so in order to really tackle the environmental impact of energy storage, we also need to closely look at Europe being globally competitive and resilient, transport of goods, access to materials, access to manufacturing technologies, and so on. So this is where we are coming from. We've realized environment is at risk. Energy is one of the key contributors to this. So how do we tackle this? So batteries and the electrification of transport is one of the big areas in which Europe has already picked up and started to improve on this in this area. So this graph here just shows how the sales of electric vehicles is really starting to take off. So this is a clear indication how policy, how legislation, and how individual perception is driving this incredible shift that we all need to face. So, however, you can't have electric vehicles without the energy storage systems, and unfortunately, as I mentioned, this is not an activity that Europe is traditionally strong at. So, so how does the Europe respond to this? So, this map changes all the time. But this is a snapshot at a certain point in time last year of all the battery manufacturing plants that were planned for Europe. So there is a significant activity in this. And as you can imagine, this opens up a lot of opportunity for local supply chains. So what is it that needs to be supplied to batteries, and how does graphene fit in? So just little basic diagram here, that lithium-ion battery, which is at the moment the most sought after battery type, particularly for electric vehicles, for mobile electronics, and so on, consists of a positive electrode, which is the cathode, that has a metal layer on aluminium. On the anode side, which is the negative electrode, you have a copper film that is coated with graphite. In the middle, you have your separator that prevents a short circuit but allows ions pass through, and lithium is what moves from anode to cathode as you're charging and discharging your battery. So in your electrolyte, you have those lithium salts. The battery is constructed of layers and layers of anode, cathode, and that intermediate separator. So as you can see on the right-hand side. So graphite here is about 40 to 50% of the volume of a lithium-ion battery. Graphite requirements for effective lithium-ion battery use are low surface area, size that is typically in excess of maybe 15 microns, that's lateral size, ultra high purity. There's no direct replacement for the graphite in the anode with graphene product. It doesn't, however, mean that graphene has no use in this space. So what is happening is that in order to make the battery most suited for a specific application, or in order to change the battery properties, the chemistry or the construction of the battery is starting to change. So currently, most of the commercial batteries have a graphite anode, and this graphite can be either synthetic or natural graphite. There are other materials coming into play, like the titanium oxides on the left-hand side. But importantly, in order to increase the energy density that can be stored in the same battery, silicon is providing this additional boost. And silicon is something that is mixed as a small part of the graphite in the anode. And already on the market, we have batteries containing a small percentage of silicon. This is likely to increase in the future years and decades. So this is an opening for what we are talking about today. So there is an enormous battery market worldwide and in Europe. Graphite playing the leading role for the anode itself, but that anode is slowly starting to change. So in order to make the same size battery, either give you a longer range, or you could maybe make a smaller, lighter battery that gives you the range that you already have. You can add maybe 5% silicon into your anode mix. This then opens a challenge, because silicon itself has some severe technical shortcomings when used as an active material. Active material means that it's able to store lithium, and then also the lithium can intercalate into and out of the material. So when you look at graphite, the lithium intercalates and comes out. There is an expansion of the graphite structure of around just over 10%, but that can still be accommodated within a battery structure. However, with the lithium, in intercalating in and out of silicon, that volume expansion can be up to 300%. So what happens when this is taking place? Your silicon particles, they expand. They can break down and create lots of small particles. Your film that you've carefully created as the electrode, when it expands, it delaminates or comes loose from one another, and some parts of your film become electrically isolated and not usable any longer. Or the individual silicon particles also, as a part of a normal battery process, generate this solid electrolyte interface, which is important for operation of the battery. But as the expansion happens, this SEI layer gets broken, it releases more fresh surface, and every time you generate more SEI, you are locking some of your lithium into that process. So this is what naturally happens to silicon. There are lots of solutions that have been offered on how to overcome this. There's all sorts of nano materials and structures, some very complicated, some less so, but that look at trying to accommodate the expansion or try to minimize the expansion by the size. However, there are multiple different solutions where graphene is either coating your nanoparticles or creating a framework structure in which your silicon particles can act as an active material without damaging the electrode structure that you have. So this is a definite area where graphene can play an important role. So what does the graphene there do? In order to so graphene can act as a coating that protects the silicon. But because it is mechanically robust and somewhat flexible, it can also create a structure that accommodates the silicon's expansion. Therefore, that breaking down of the silicon particles or that breaking down of that electrode layer, creating those insulated areas can be avoided. Because it coats the material and perhaps can slide around and rearrange a bit during expansion, it can moderate the formation of the SCI and keep it minimized so that the lithium that is locked away from the active use in the battery is minimized. Also, the conductivity that graphene possesses inherently can also improve the electrical conductivity of that electrode layer and thereby increase the cycle life and the rate capability that are both related to the conductivity. Also, it's important for safe use of batteries that there are no hotspots inside the battery while you're operating. So the thermal conductivity characteristics can also stabilize the temperature of a battery and improve the heat dissipation. So there are many positive aspects of graphene that can really help make silicon more usable within a lithium-ion battery anode, and therefore give us that advantage that we need for electrification of transport, for example. Going further, graphene is a highly conductive material. So there are many areas of energy storage where conductivity is required. So whether you are talking about the silicon anodes or in a lithium-ion battery, the metal oxides on the cathode, but also across all other types of battery materials, batteries and lead acid, whatever you name it, their electrical conductivity really significantly impacts how long you can use a battery and how quickly you can charge and discharge it. So what happens in the battery manufacturing is that you often, particularly with silicon anodes and with cathodes, you add some conductive additive materials to make sure that the electrode remains conductive enough. Often this is done with carbon black. It can be done with graphitic carbon as well. It can be done with carbon nanotubes. But graphene offers a good solution here because the impact on the rheology of the slurry that you use to make that coating is less impacted than, for example, with nanotubes. So what you want is this conductive network throughout your electrode that can ensure that your conductivity remains sufficient. Also, if you have a high internal resistance, the reactions that happen at the surfaces of your electrode materials can shift, and this is called polarization. The process that happens, it's quite complicated, but what the conductive additives can also help with is to decrease the negative effects and enable to have a system where those chemical reactions are more optimized. Additionally, as batteries for commercial use need to carry more and more energy, the electrodes that when they are prepared are pressed into very, very dense thin films. So as you increase that what is called calendar density, you normally reduce the ionic conductivity through that film, which is an important part of getting your lithium to move in and out. So conductive additives have also been noted to create small amount of additional porosity that helps facilitate the ion diffusion. So conductive additives, exactly what graphene is good for. There are many areas in energy storage where they can come into play. This is in battery sector. So just before I conclude, just talk a little bit about next generation technologies, because lithium-ion batteries are on the market. They are a market leader. Silicon is already available in in some commercial batteries, maybe in the form of silicon oxide or silicon carbon composite. But there are many other battery technologies and energy storage technologies and even energy generation technologies where graphene can come into play. So just to sort of highlight a few of them. Sodium-ion batteries. This is an area of huge amount of development at the moment because sodium is much more abundant and cheap compared to lithium. And there may be some good safety elements that would come into play for using sodium-ion batteries. However, graphite, which otherwise offers a good active anode material, is actually not usable here because sodium ion is so much bigger than lithium that it does not intercalate effectively into graphite. So three-dimensional graphene structures, for example, or graphene structures with spacers have been investigated and shown to allow the sodium ion intercalation. There are also some sort of further in the future technologies that are being developed that also benefit from graphene from the high surface area, whereas in the lithium-ion battery that is not terribly advisable, or it doesn't provide a benefit, rather maybe the opposite. But in these other battery types, a very high surface area with combined with chemical stability and conductivity can be really interesting. So there are, for example, metal air batteries or lithium sulfur batteries as examples here. The good thing about the graphene aerogels and also for the supercapacitor electrodes is the ability for graphene to generate either just dots, one-dimensional structures, or lines and rods and these 3D networks as well. So without having to add a significant amount of stabilizers that otherwise would reduce your conductive properties. So there are lots of opportunities in electrodes where you need high surface area and chemical robustness and the ability to make these different new structures as well. And finally, solar energy. So energy generation. So very interesting project that you can find more information from the Graphene flagship website is a program where graphene monolayer is added onto a perovskite silicon solar cell structure to enhance the performance, to make solar energy more efficient. And so there is this large scale solar panel field being generated and this idea tested out. So lots and lots of different opportunities for graphene in energy, from storage to generation and transport as well. So I hope this gave a flavor. It didn't cover everything and it didn't cover things in a huge detail, but I'm happy to answer questions related to any of the topics discussed today later on. Thank you.
Thank you very much, Anna. I can't speak for everybody else, but I think for me this was already like a lot of flavors, and I'm looking forward to discussing in further detail. I'm just going to start sharing my screen again in a second. Okay, and the last area we wanted to talk about today is also a hot topic. One that definitely has been right and left and center over the last couple of years, which is healthcare. Another rather important one, another of the Sustainable Development Goals. And in this case, we know that, for instance, in the EU, the primary competence for healthcare is left to the member states, with the EU playing a complementary role. But a few of the activities in this complementary role are actually quite relevant for technology, because the key objectives of the current Commission include improving patients' access to innovative medicines and medical devices, as well as increasing cooperation on health technology assessment. HTAs are overviews that some member states have started carrying out to assess how innovative medicines, innovative medical devices can perform better than the ones that are currently in use. And so This is very relevant, talking about graphene and innovative technologies. So I will hand over to Vincent Bouchiat, who is the CEO of Grapheal, who will talk us through what graphene can do in the healthcare sector. So Vincent, whenever you're ready, the floor is yours. Thank you.
Hello, everybody. Do you hear me correctly?
Yes, we can hear you.
Okay, thanks a lot for this invitation. Do you see my screen correctly?
Yes, again.
Okay, thanks a lot. So it's a wonderful opportunity to show you what we are doing at Grapheal. So Grapheal is a very young and small company yet, which is created from a spin-off from academia for French Research Center in Grenoble. And our main motivation is really to get the technology out of the lab, pushing the envelope to something useful on the market. And we are working on graphene for the last 15 years, from the very beginning of the graphene discovery. And we have identified healthcare as a very promising field for graphene. And I will try to show you why we're doing that. So as I said, it's a small spin-off of CNRS deployed on 2 sites in Grenoble. Grenoble has a lot of potential in this material. We have a lot of biotech industries, nanotechnology centers, and I think it's a wonderful place to start this venture. I've been working in academia in Yale Institute, which is a physics laboratory doing solid-state physics and material synthesis, and the company is still headquartered there. And we've been opening some biotech lab in an incubator on the other side of the city, just in front of the university hospital. So we have 10 employees, mostly R&D, 6 PhD and 8 nationalities different. And we've, at the moment, working to actually increase the activity and build the first pilot line to show that the product can be produced at large scale. So biomedical application of graphene is a very wide field, and it's not my intention here to give you a full picture of that because it will require hours of seminar. I want to tell you that we are focusing on 2 subparts, which is biosensing and tissue engineering, and we would like to combine those in hopefully the same product at the end of the day. So there are other potential effects of graphene for tagging, for quantum dot tagging, for drug delivery, gene delivery, targeting tumor cells, and so on. And it's just the beginning, I would say. So we are working on a very specific material, which is a continuous monolayer of graphene, exactly 1 layer, which is macroscopic and which is supported on an insulating polymer membrane. So it's looking a bit like that. So the production of this material is much more difficult compared to flakes that can be produced from graphite. It's produced by microelectronic chemical vapor deposition on a catalyst, basically a copper foil, and we decompose some hydrocarbon at high temperatures, typically 1000 degrees C. Methane is used as the carbon source, which decomposes on copper. It used to be very expensive stuff, and the cost of the material used to be in the range of €100 per centimeter square. But the nice thing is that thanks to the push, not only by the graphene flagship in Europe, by the input from big corporations involved in semiconductor industry in Asia and in the US, in China as well. So we've got a huge fall of the price, which is now a few cents per centimeter square, which make it compatible with disposable product like the one I would like to put on the market. So the fact that now we have good materials at low cost is really the main point that makes the system ready for the market. So the way we do that, so we have the production of graphene as a thin veneer of a monolayer on top of copper. And then you have to, of course, delaminate and remove all copper residue from the graphene. So we have a proprietary process for that. We evaporate a polymer on top of the multi-layers. And then we're going to etch or separate some. We have also a delamination process that you can recycle copper. And we get system which is reversed upside down, where graphene is now towards the top surface, which is supported with a biocompatible polymer. It's important to say that graphene is fully continuous. It's a polycrystalline mosaic of monocrystal without too much multi-layers. And that you can put in bondage, as we're going to see, for example. So what is graphene about here? We have a combination of property which make it quite unique. I made a lot of study before creating the company that's indeed biocompatible, and that's even on the skin for several days. It does not interfere badly with wound healing, for example, and it can be put on an healthy skin as well. It's transparent and ultra flexible. It's completely conformal with the skin. And more interestingly, it's a very good electric conductors without any too much defect on it. And even more important is that the resistivity on the surface depends on the liquid composition on top of it. And you can actually put some chemical at the interface to really orient the sensitivity towards a given analyte, towards some biomarkers. So, as I said, we looked a lot at non-toxicity of the material and the fact that there is no release of nanoparticle even after 3 days inside the wound on a pig model here, for example. So the first study we did was actually growing neurons in vitro on it. And it was some kind of academic studies, which gave here, as you can see, several publications. The nice thing is that you have transparent electrodes, which you can probe in plane in between electrodes. On the top part, you can do microfluidics. You can inject and you can probe with top electrodes, for example. And on the back, because graphene is transparent at the difference of silicon, you can really see through and you can actually monitor with an inverted microscope the evolution of the cells. Here you can see, for example, some activity which is probed by the graphene transistors, often neural networks coming from mice, which has been grown in situ during 3 weeks on the graphene transistors. And you see clearly some activity that you can suppress by injecting a toxin in the liquid, for example. The FET, which is the feed effect transistor you can make, is exactly similar to what you can do with the other type of semiconductors, except that because of the absence of a band gap, you have a kind of V-shaped instead of having just one side which you put the system on. So this V-shaped structure is really the hallmark of graphene transistors. And you can see we can make it rather reproducible on the scale with some integration here. So the reproducibility is quite well, even on plastic, glass substrate, and so on. So also we made some in vitro studies. Here you have a coating of an implant for brain activity monitoring, which is done on the mice again. And as you can see, this is a commercial implant made of silicon electrodes, which is commonly used for probing activity. After 3 weeks inside the brain, you have the production of inflammatory astrocytes, which is detrimental for the probing the activity because basically the active neurons recess. And because of the inflammation, actually, you lost the connectivity. With graphene-coated sample, the same type, exactly, but just with one layer of graphene on top, you keep the activity probing because of the good conductivity of graphene, and you remove significantly the adverse inflammatory response because of the bioacceptance of graphene. And that gives a much reduced inflammatory response here. So that's another proof of the very nice biocompatibility of the graphene layers. So we have all these good indications. So what we want to do to go to the market, as you can see, and what the pandemic showed the last couple of years, is that there is a big need of medical diagnostic on the field at the point of use. Today, you have a lot of different type of device with, of course, very basic ones with lack of precision, lack of reliability. You have on-site test strip, which are quite better reliable, but slow and very difficult to integrate in a digital process, which means manual processing, manual entering the result. And there is a lot of problem of networking of this medical result. You can have, of course, much more advanced PCR-like devices, but they have a high cost of ownership. They use expensive consumable, and they are very difficult to deploy on the field, typically, for example, at the entry of an airport, for example. So there is a very big need of diagnostic tools on the field, either for hospital at home, remote patient monitoring for chronic disease, or for sanitary screening at large venue, for example, for this pandemic. So how graphene can help for that? Well, what we found is that we can make sensors, flexible sensors, easy to produce massively. You can functionalize it to target given biomarker, and you can couple them with RFID so that smartphone technology can easily integrate with them. So we start with two applications of that. The first one developed is a soft patch which you can put at the edge of the wound that will monitor the wound evolution in time and gives patch after patch, when you change the bandage, a full history of chronic wounds, the wound of elderly or diabetic people that can stay weeks or even months before healing. And it's very important to follow that, I will see in an instant. The other one is a digital test strip that we have developed for the pandemic, which give in a few minutes, 3 minutes exactly, a digital pass you can use to access a given places for a given time. So for that, we combine, of course, the graphene bioelectronics, which I've shown you before, which is easy to deploy with plastic electronics, printed electronics. You use, of course, the interconnectivity and the interoperability on the full platform of NFC. The NFC is used, for badge access. It's also used for payment, for secure payment in smart card technology. Now you have it integrated in the both Apple and Android ecosystem. It's very cheap, it's very secure, and the chip which is embedded on the other side is extremely cheap. You can have a €1 chip, for example. And of course, you will take advantage of the starting and the emergence of telemedical science. So the way it works is that you put on the layers a biochemical that will actually make an electrostatic signal that the graphene will sense. You can have pH sensors, which is important to follow the evolution of a wound, or you can have given biosensor, for example, targeting the biomarkers responsible for the COVID infections. So you can detect a lot of things with that. The most important part is the functionalization of the layers. It can be ionic potential, pH. It can be small molecules such as hormones, DNA hybridization for genomics, protein and viruses, and even bacteria on a very wide range, depending what you put as a probe type on the surface. So for the case of the graphene wound patch, we have a completely integrated structure which is flexible. When the graphene is in contact with the wound, there is back electrode measuring this resistivity, an antenna which is connected to a system on chip that will power, without the need of a battery, the electrodes and the graphene sensor and the system of communications. So in the case of wound lab, you have this system that will be monitored and configurable by the nurse. The nurse will have some data she can send back to the data transmission system, some telehealth system, that given the signal, we can give back an alert in case of infection, such as a large and rapid change of pH and temperatures. And that is important because without opening the bandage, you can monitor directly the wound evolutions. That's typically how it works. You approach the system and you directly communicate and download the data. So this is healing tracking is quite important. And we would like also to combine it with electrostimulation, which is known to actually accelerate wound healing, and to combine the diagnostic activity with some therapeutic one in the same device at the end. I want to speak on the other one, which is, has been recently highlighted by this Innovation Award at the CES. So the way it works is rather similar, even though the technology under the hood is the same, it has a complete different use case. Here you have the capability to actually make the system personal. So for example, you can use a selfie to make the system locally without transmitting any information on the network, so which make it GDPR compatible and compatible with the stringent personal data protection laws in Europe. And the system has this biosensor. Depending on the detection of biomarkers, it gives a signal that can, in several minutes, open access to a digital pass, giving on the e-paper here the capability to provide a QR code for a given access during a given time. So you don't need to have intervention after the system is done. You throw away the sensor, which is kind of a USB key. You can keep that for a given time as the digital evidence that you've made the test, and you can redo another one by plugging again another sensors. So the way it works is rather simple. You cover it with an antibody the graphene surface. There is a reaction of the biochemical recognition between protein of the virus to the system. It's given a change of conductivity of graphene, and the change of conductivity when it goes beyond a certain threshold give a positive or negative results. So you have here, for example, the response given the amount of protein responsible for the positivity of the test. And you see we have a level of detection of 10 nanogram per milliliter, which is similar to the antigen test on the market. So why graphene are indeed useful for this electronic health product? Graphene biosensor combine in the single device unique property. They are flexible and biocompatible. They are actually transparent, you can see through. They are versatile, they are sensitive and fast, easy to integrate, and compatible with printed electronic without clean room need to make them working. So that you can make them for a few euros. And they have a low environmental impact because we really want to reduce the number of components. It's a system which is rather simple to biodegradable, and there is only one chip, a system on chip for probing them. So it's quite cost effective as well. So that's really what we propose as a use case for graphene, hopefully going to the market very, very soon. Thank you very much.
Thank you, Vincent. That was also very interesting. And I think we can jump straight into questions to see if anyone from the audience would like to ask anything. And actually, while people think of a question or check whether the microphones are muted or not, I'll just go back to Terrance perhaps and ask a first question maybe. So in the next steps for the framework and the ISO standard, you mentioned sustainability and the work on footprint, which I found very, very interesting because, as you mentioned, a lot of companies are taking commitments to go into net zero. But there is also, in Europe, we have the a stakeholder consultation ongoing for the targeted revision of the REACH regulation. And one of the questions, I found it pretty interesting, is asking respondents to see whether they agree or not with the potential idea of starting to request information about a substance environmental footprint when you register it, so when you file a dossier. So this is very, very relevant, I think, and very, very useful for companies. So maybe can you talk a little bit more about how, if you have already an idea of how this work would look like and how long you expect it to take, if you have any more details on this?
Sure. So maybe the first place to start, the impetus for this is that major companies like a BASF or such are going to demand this kind of information from suppliers, right? So you'll start with major companies that are asking for this kind of information. On the regulatory side, I think it's a tremendous burden to put on more companies for the registration, simply because there's no codified methodology for actually measuring the carbon footprint. And you have all sorts of variables, such as where in the value chain do you start? So for example, with graphene, do you start with the mining of the graphite material, or do you start with the pre-processing? You know, what part in the value chain do you start to measure the energy inputs and such for that? Now, having said all that, I think we don't have to wait for somebody else to devise the method for us. I think we can put some good thought to this, and we can talk about how to measure this, and we can come up with our own framework that if it needs to be changed later, we change it later. But for example, with graphene, you have a method of mechanical exfoliation, which would be relatively easy and straightforward to measure the energy inputs. You have the modified Hummer's method, so you have other ways of measuring that. And I think it should be, quote unquote, relatively easy to measure the carbon footprint of manufacturing graphene. What we are going to advocate, though, is the end use application to measure the true impact. And I don't want to talk too long, but I think this is a really important point. If you look at graphene and how it's added, for example, into concrete and cement applications today, it's in hundredths of a percent by weight. But with graphene added to a metric ton of concrete, you can remove up to 9 kilos of carbon by using grams of graphene. So even if you had the dirtiest process possible to make graphene, the net effect is tremendously positive. So if you just looked at production, you would say it maybe has a bad, quote unquote, bad carbon footprint, but that's not the right picture. The right picture is how much carbon can we save by using graphene? And then you look at the net effect. That's the approach we want to take.
Yeah, thank you. And that makes a lot of sense. It reminds me of the same approach taken in the digital industry, where they argue that adopting digital solutions can help you, for instance, in smart agriculture to improve your efficiency in energy efficiency, monitoring the energy consumption of your building, for instance. So the net effect is actually a benefit. So I have a question in the chat. What challenges do you see in graphene quality assurance? I assume this might be for Terrance, but perhaps we can just go and ask it to the speakers in turn. So Terrance, I'm just going to ask you to give your answer, and then perhaps if Vincent and Anna have anything to add, we can see with them as well.
Sure, I'll try to be very brief. The Graphene Classification Framework is meant to help be consistent in testing methods and what we test for. So that's part of quality assurance. And the other big issue with quality assurance for graphene, because we don't take a position on quality, we take a position on accurate measurement. But the quality assurance, a big issue is repeatability. To be able to produce the same material consistently is a key challenge. And that means you have to have consistency in measurement techniques. That would be my response.
Thank you. Anna, perhaps you want to add anything?
Sure. So I agree fully with Terrance that measurement techniques and the way you prepare your samples have an incredibly important impact on your measurement results. So there is a lot of development that is needed to be done in that space to have standard measurement techniques available that are accessible to producers and end users, because that's the other area that is not always easy. I also think that that from the end user's perspective, quality of a material and the performance in your intended use is not a straightforward process to understand, and to so I think that is the bigger challenge, because even manufacturer of a very similar product may have slight variations in their process that will impact what kind of raw materials, if you consider graphene a raw material, you need to use. So I think that unfortunately I don't think there's a shortcut for this. There is a direction that the work of Graphene Council can give in helping you start from the potentially the most suited types of material, but I think there is still a lot of development work that is needed as well, which can sometimes be time consuming. It can also be expensive. So I think that's probably, in terms of graphene applications in everyday products and life, is still something that unfortunately is challenging.
Mm-hmm. Yeah. Vincent?
Yes, I would like to add regarding your range of product we are envisioning. So, we have the responsibility to make graphene in a medical device. So we have to define something like medical grade graphene. We've seen that graphene exists in so many flavors, so many range from flakes to continuous monolayers. So some of them are biocompatible, others are not, depending also on the oxygen level. So it's very important to be sure about the quality of what we are making. So having online quality control using the probe, and which has been shown by Terrance, is very important. And we have this responsibility to really control quality indeed at the molecular level.
Thank you. I also have a question that is probably slightly related to that for both Anna and Vincent. You mentioned obviously quality and the trust and confidence obviously of the end users. So I was thinking in terms of challenges to successful commercialization, is there a role of what role does perception play? Do you think that there is a problem of perception to address? And also, does regulation pose a barrier? Because obviously for batteries, for instance, and also for these very innovative type of medical devices, the problem with innovation sometimes is that you have regulation that was developed years and years before and does not necessarily take those specifications into account. So it might be an obstacle. So I was interested in hearing from you a little bit about what kind of barriers you see to commercialization.
Yeah, maybe I can answer about the medical device part. So, in the case of our product, you see the graphene is indeed a nanomaterial, but it's actually a veneer on top of micro layers, typically 10 micron thick layers. So if you don't have nanoparticle leaching out and the system stay, with this full integrity, it's more like a nanoscale varnish on top of a layer, which already exists in many materials in the industry as thin film coatings. So then you can really go back to some classification. Of course, if you have release of nanoparticle, which could happen, then you have to show it's below a very little range, because we have a monolayer of carbon. So the amount of material leaching out will be extremely small at a trace amount. And if we show that we are below a certain amount of nanoparticle, then also we can be on the safe side. But it's very important to really have a good case about this. The amount of nanoparticle we produce will never be big in that case.
Mm-hmm. Yeah.
Yeah, I think it's quite different for an area like batteries, where we are talking about bulk quantities of materials. So the battery legislation at the moment talks a lot about battery safety. So there are some performance criteria that batteries must meet, and very stringent safety criteria. In Europe and actually worldwide, what is not very well regulated necessarily is or standardized yet are the criteria and the specifications for the materials themselves. So at the moment, how it's taken is that there are some specifications in Asia, and I'm sure more underway in development. But for example, impurities are considered a very significant risk to safety. So I think that there is in terms of all battery materials, but nanomaterials in batteries in particular, I think that the opportunity is there, as the material characteristics aren't fully defined and regulated as of yet, but one needs to be able to ensure that all the full safety criteria are met, and that can be quite challenging, because yet again we are facing this long-term validation programs that will be needed for all materials entering the battery industry.
Thank you. I think we have time for one more question if anyone from the audience would like to jump in. Oh, it seems we have a shy audience today. I'm going to add, Terrance, can I throw a slightly difficult question at you?
Of course, yeah.
Yeah. Okay, thank you. So it's just because, so yesterday we had a different event that was looking at something quite different, the implementation of OECD test guidelines and their use from industry. And one of the, so we surveyed participants about different aspects of this, and one of the things that came up was that there is obviously some like industry is a bit divided when it comes to using OECD test guidelines versus an ISO standard. There's different pros and cons and different factors influencing the decision, of course, but one of the things that was mentioned as a potential obstacle to the adoption or like to the use of an ISO standard is obviously the fact that unlike the OECD test guidelines, you have to pay for a standard. And so I was wondering, so you obviously have now passed the copyright onto ISO for the classification framework. I suppose the potential impact of the fact that you now have to buy the standard was already kind of priced in your decision, and you do not really anticipate that this would impact industry's willingness to use it.
So I appreciate the question. It's actually really useful. So the license we gave to ISO is non-exclusive. And they know that we're actually in discussions with IEC and also ASTM for the standard. Okay. Also, the Graphene Classification Framework and how to apply it is publicly available for free, okay? So that will continue to be free because the Graphene Council continues to own the copyright outright. We simply gave a license to ISO if they should choose to convert it into an international standard. And the other thing I would comment on this is our experience has been that different industries and different players use different sets of standards. So for example, in ASTM, which is an American organization primarily, or you look at IEC, or you look at ISO, or you look at BSI, they have very similar standards in many areas, and you would think they overlap. But in fact, it depends on what industry you're in and who commonly uses those standards. So I think this is a case, if OECD wanted to use our graphene classification framework, for example, they should simply let us know, and I'd be happy to engage with them, because our intent is to make this as widely available as possible and make it publicly available. And ISO, if they wish to put it into an international standard, the advantage, of course, is it goes through their own internal peer review process, and it carries more weight than just coming from the Graphene Council. As much as we'd like to think we're the, respected authority on this, I don't think we're the same as ISO.
No, of course, and that was indeed one of the advantages mentioned during yesterday's discussion, and also the fact that that process is quite faster. When I look also at the speed at which you developed the classification framework versus how long it takes for OECD test guidelines to be approved, for instance, it's quite impressive. All right, so we have reached half past the hour. So I would want to thank our speakers again very much for their interesting presentations, everybody for participating. And as we mentioned at the beginning, you will receive the link to the recording once it is available on the NIA YouTube channel, as well as the slides. And of course, if you realize that you did have a question just as soon as the connection is closed, please do not hesitate to send us an email. Otherwise, thank you very much and have a nice rest of day or afternoon. Speak soon.
Thank you.
Thank you, everyone.